Hello everyone. In this video, we're going to discuss this problem D, returning home from the Codeforces round 675 div 2. So the problem is that we are given an area of n into n square blocks, and then we have to move from the source to the destination coordinate. And in 1 minute, we can move either to the adjacent blocks from the block where we are currently in, or we can move to some magical locations, which there are m magical locations, and that magical location we can instantly go to that magical location without passing the time if and the magical locations are such that if we can go to the magical location only if our one of the coordinate, either x or the y, will coincide with the magical locations coordinate. And then we have to find in this situation what is the minimum time we need to get to the destination if we are having such magical blocks and we are giving this n into n square blocks. So the constraint is that our n is from 1 to 10 to the power 9, that is huge, and our magical location number is up to 10 to the power 5. So we can use this information that we will can use to solve this problem. So let us try to understand this problem in the whiteboard. For example, in the first example, we are given that we will go we have to go from 1 to cross 1 to 1.1. Let us assume that this is 1 comma 1. So from this point, which is our source, which is 1 comma 1, we have to go from source, which is 1 comma 1, to destination, which is 5 comma 5. So let us say the destination is here, which is 5 comma 5, and we have some magical locations in between these two cities. So which is at the point 1 comma 2, which is here at 1 comma 2. So at here this is 1, right? So one magical location is at here, which we can call that m1, and then there is another which is 4 comma 1. So this will be like here. We can say this to be m2, right? So m2 be 4 comma 1, and there is another one which is at the location 3 comma 3. So which will be around here, yeah, m3. So what we can do is in this problem, in this situation, that we know that we can directly come from here to this magical location in no instant of time. So it will take 0 time to come from here to here, and then from 4 comma 1 we can go to 4 comma 2, and then from 4 comma 2 we can go to 5 comma 2, and then from 5 comma 2 we can go from 5 comma 3, and then from 5 comma 3 we can go to 5 comma 4, and then 5 comma 4 we can go to our destination 5 comma 5, in total of 1, 2, 3, 4, and 5 seconds, right? So in this way we can reach here. So now let us try to understand how we're going to solve this problem. This is the example which will help us to know the problem statement, but now let us try to understand how we can solve this problem. So now we should try to understand that we have these magical locations, right? So let us say we have this arbitrary magical location here, here, and here. Let us say take 3 magical location. Let us take this to be the source, and let us take here to be the destination. Now what we can do is we can say that we can connect this magical destination through edges, and we can build a graph upon this, right? And what we will do with the help of this graph, we will compute the shortest distance from the source to each of these magical locations. Like how we'll compute the magical location, the shortest distance from for each of the magical location is like if we compute, let us say, the shortest distance from the source to this magical location m1, then we can easily compute the shortest distance, whether this will be from here to here or from here to here, shortest distance from s to m1, and then m1 to m2. So it's like similar to the Dijkstra algorithm, in which we compute the shortest distance. So whether this will be this or this will be the summation of this part and this part. So whether this will be this or this, right? So now let us just remove this edges. So now we have to build the edges, right, in the between the magical locations. But we have total m magical location, which is up to 10 to the power 5, right? So if we build the graph uh, between a magical location, each of magical location to each of other magical location, it will be order of m square, which will be a lot of edges. So, but we need to understand this thing that if we build, let us say the edge between m1 to m2, and then we want an m2 to m3, then if we build m1 to m3, that will be a waste of edge, because we can go from m1 to m3 via m1 to m2, and then from m2 to m3, and it will take exactly the same distance to go from m1 to m3 if we go from m1 to m2 and m1 to m3. Why is it so? Let us try to prove this thing. So let us take the distance between m1 to m2. What will be the minimum distance between m1 to m2? The minimum distance between m1 to m2 is whether the difference between their y ordinates, because when we reach this y ordinate at position here, we can quickly come to here at no time, or the distance between their x coordinates. So the minimum distance will be one of the two, right? What we can do, we can assume that like here it is visible that it is y, but for the other examples it will not be visible. So what we will going to do is we will going to connect m1 to m2, which are nearby points, compared to m1 to m3. And how will we know that these are nearby points? We will going to sort these points with their x-axis, with their x coordinates, and with their y coordinates, to make sure that they are near, so that we are connecting the only points which are near to each other. So we can say that we are connecting this edge m1 to m2 based on their difference in the x coordinates. And also we will going to also build another edge, which is these edges are undirected edges, which is, so the cost of this edge of m1 to m2 is delta y and delta x. Similarly, we will going to construct another edge which is having delta x here between m2 and m3, and similarly delta y here between m3 and m2 as well. So we should try to understand. In this example, I have taken the coordinates as such that their axes are also increasing in this direction, and the axes are increasing in this direction, and also their y's are also increasing in this direction. Like I have taken it like in the sense that y is equal to x, like in that kind of direction I have taken the coordinates to understand this example a little bit easier way. So we will construct the edges between the neighboring points sorted by their x and their y's. And let us say, like if we have constructed this edge, for example, delta x and delta y, we know that this delta x is less than delta y. Like delta y here in this case is less than delta y. So we should always traverse the graph from m1 to m2 via this edge, not this edge, because that will kind of like increase the cost to reaching from m1 to m2. Like then we can compare then from s to m1, that is the edge from s to m1 plus m1 to m2 via delta y, and then we can also compare it with s to m2, and we'll see that whatever be the less, we will take that for our answer, right? So, and how we'll compute the distance between any two points? We will simply compute their Manhattan distance. What is the Manhattan distance? Manhattan distance is the distance, like for example, here to here, there are 2 points, which is P and Q. So the Manhattan distance between these 2 points will be simply the differences in their x plus the differences in their y, right? So this way we'll compute the Manhattan distance, and we will compare the Manhattan distance from S to M2 with the distance from Manhattan distance from S to M1 plus M1 to M2, which we have just created this edge M1 to M2 via delta y and delta x, right? So yeah, this is Manhattan distance. So in this way, we will construct edges and then sort it on their x and y's, and then we will gonna put these edges in a priority queue, and we will take the distance, the edge with the minimum distance first. We know that priority queue will give us the maximum element first. So the way we're gonna extract the minimum distance, we will gonna put a minus sign in front of distance. So make sure that if the distance is least, the minus sign will be a minus sign when put it in front of it will make it more. And in that way, we will gonna extract only the largest, like the least distance part. And also we will not gonna visit each node again and again. For example, here we have visited this node, and then we will visit this node via this delta y. So when we will also get this delta x, we can also reach since from delta x as well, but that will increase the distance, and this will visit this like the later on, like it will visit it after it visit via the path delta y because of the priority queue properties. But since it is already visited, we will not then visit it via delta x, right? So in this way, we will want to not visit the root, visit the node again, even if they are connected by two edges via delta y and delta x. This is the general, like one of the case which can show that thing. So yeah, I think now we should understand the code to also understand it a little bit more better. But and also there is one thing more. When we'll compute the shortest distance from the S to all of these locations, let us say M1, M2, and M3, then what will be the answer? Answer will be the shortest distance between M1. The initial answer will be the Manhattan distance between the source and destination. So we will compare that initial answer to our to the shortest distance between S and M1 plus the Manhattan distance between M1 and D. Similarly, shortest distance between S and M2 plus the Manhattan distance between M2 and D. Similarly, the shortest distance from between S and M3 and the Manhattan distance between M3 and D. Why it's so? Like why we have to kind of like compute the Manhattan distance from the these points to the destination? Because like I can prove this thing, because let us say that there is some other magical location which will come like we can, for example, let us say this is the shortest path S M1, and then we can directly go to this path this magical location, and then we can go in the destination via this Manhattan distance, right? So not to this but through this, right? So yeah, so through this we will go. Okay, so through this we will go, and so but now so it means that we are wasting this additional distance m1 to that location distance. But when we computed the distances, right, then whatever is the distance from this point to S to M1, it will be the same for S to MI as well, because M1 and MI are connected by zero cost edges. So it means when we compute the answer, so when we compute the answer from S to MI, then it will be less, like it will be equal to S to M1, but this distance M1 to MI will be saved, like when we compute the Manhattan distance from MI to D. So in this way, we'll want to save that additional distance as well. And so we will not have to compute again the shortest distance between each of these points to the destination. We can just compute only once the shortest distance between S and all these magical points, and then just take their shortest distance plus the Manhattan distance, and whatever is the minimum of those, we will take that to our answer, right? So let us now look at the code to understand it a little bit better, right? So in the code, what we are doing is like, we are first of all, we are inputting our NNM, and then we are inputting source and then destinations, and then we are initializing our answer to the Manhattan distance between the source and the destination, and then we are having the vector of x and y coordinates. But now what we are going to do is we will want to have order vector which will sort the indexes of the from 0 to m minus 1 according to the values of x. That is, the value x which is less, that index will come first, then the value x which is more, that index will come later on, right? So then what we're going to do is we have a vector of edges. This vector will have two, like the edges will have the true properties. It will have the like the from and to nodes, and also the weight of the edge from or to. So what we are going to do is like we are in the edge we are putting this index ai, and also the next index ai plus 1, that is the neighboring index, that is the neighboring index here, and also the weight of the edge which is their x, x of the index I plus 1 and x of the index I. Similarly, this is that since this is undirected edges, so we will connect vice versa as well. Similarly, we will want to sort according to the y, so they are neighbor to each other, and we will also construct an edge between their y's as well. So it may happen that some nodes will be connected by two edges, like because they are near in the x and near in the y as well. But we will going to take that edge only, which is the least cost edge. Then we're going to have a priority queue, and we'll have a visited array, so that we will not visit the same node again if we have two edges going to the node from some node. And we'll also have this distance array which will store the distance, shortest distance from for each of the magical points from the source. So what we are doing initially, we are initially putting the values of the Manhattan distance for each of the points, because that is a distance we can compare with to the shortest distance if there is any. So what we're going to do is we will going to extract the topmost element of the priority queue, and the topmost element of the priority queue will have the least distance because we are putting this minus sign, this minus sign. So that's why then we will gonna say if this is visited, we will not do anything. Otherwise, we will set visited to 1. And then since we have put the distance to minus, so we will set distance equal to minus of distance, and then we will set the index of the distance to distance. And then we will go to each of the neighbor and their weights of that index, and we will gonna put the distance plus the weight as we do in the Dijkstra, and we will also put the index of the neighbor in our priority queue, and then we're going to repeat this process again and again till we achieve all the distances or till we achieve all the visited index to be 1. And after that, what we are doing is like we are saying that the answer will be whatever answer we have initialized first, that compared to the distance of each of the indexes I, which is we have computed the shortest distances plus their Manhattan distance from the destination, and whatever be the answer, we will output that answer for in the output. So thanks everybody for watching. With this note, I will terminate now.